Hi, in this lesson, we're going to learn how to solve three equations with three unknowns. And we're going to do this by Cramer's rule as well as elimination. But before I can show you Cramer's rule, I have to show you how to find the determinant of a 3 by 3 matrix. Remember, a 3 by 3 matrix means that you have 3 rows and 3 columns. Again, when you have the same number of rows and the same number of columns, that's a square matrix. And there are methods to find the value or the determinant of that matrix. So I'm going to show you a method that's used often, and then I'll show you a different way to do it. So this first method is more of like a trick. It's kind of like not the most mathematical way to do it, but it's probably the quickest way to get your answers. So here we have to find the determinant of A, where A is the matrix that you see here on the right. So the trick involves repeating the first two columns and writing them to the right of the matrix, which is what you see here. So it's the original matrix, same 3 rows, same 3 columns, but column 1 and column 2 are written again to the right of the matrix. Then the technique to evaluate it is what I'm going to explain right here. You start from the upper left-hand corner and multiply on a diagonal. So the first product is 2 times negative 2 times 3. That's what you're seeing in this line. Then you go to the next diagonal with 3 values. Negative 1 times 4 times negative 1. That's the next product that you see. And then the last diagonal of 3 numbers is 0 times negative 3 times 1. Then you repeat the process, but you go in the other direction. When you go in the other direction, you're going to subtract the products. So the first product that I am subtracting is 0 times negative 2 times negative 1. That's what you see here. Then you go over to the next diagonal to the right. So that's 2 times 4 times 1. That's what you see again on the line below. And then the last one, the last diagonal of 3 numbers is negative 1 times negative 3 times 3. And that's written again on this line. Then you multiply these products out, which is what you see on the second line of work here. So that gives you negative 12 plus 4 plus 0 minus 0 minus 8 minus 9. When you do all of that addition and subtraction, you get a determinant value of negative 25. All right, so let's practice that again. Here in blue, I have another 3 by 3 matrix, and we're going to find the determinant of it. So again, the trick is to repeat column 1 and column 2 and write it to the right of the 3 by 3 matrix. And then you start in the upper left-hand corner and multiply the 3 numbers on the diagonal. So the first diagonal that you have is 0 times negative 2 times 4. That has a value of 0. I'm just writing down the product. Then you go to the next diagonal, negative 1 times 1 times 5. That has a product of negative 5. And remember, you're adding when you're going from left to right. Then I have negative 3 times 2 times 3. That gives you a value of negative 18. And again, so you're adding negative 18. Now we go in the opposite direction. So again, going back to the original matrix, the first diagonal that you see is negative 3 times negative 2 times 5. And when you're going from right to left on a diagonal, that's when you start subtracting the products. So that's why I have minus 30. Then 0 times 1 times 3, well, that's minus 0. And then negative 1 times 2 times 4, well, that's minus negative 8. Okay, so I'm just going to rewrite my pluses and minuses appropriately. So the combination that I have to put together is right here, negative 5 minus 18 minus 30 plus 8, and that gives me a determinant value of negative 45. Your determinant could be negative or positive or even 0. So now I'm going to show you a different method. This is like the more mathematical way to do this. So there's a couple of things you have to keep in mind with this other method. So with this other method, you're going to pick one row or column, and that's going to kind of be the dominant row or column that's going to determine what you do next. And it doesn't matter which row or column you use, but anything that has a 0 in it will always be easier, less work to do than non-zero rows or columns. So if you have a 0 anywhere in your matrix, you want to pick a row or a column that has a 0 in it. If you don't have a 0, then pick the row or column with the smallest numbers. Or any row or column that you want. Another thing to keep in mind are these signs here. These signs, notice that they start with a plus and then they alternate from plus to minus all throughout. And that will be important again in terms of setup. So I'll refer to that in about a minute when I actually do an example. All right, so we're going to evaluate a determinant where your determinant is A that you see here. And I have a 0 somewhere in this determinant. And the 0 is in row 1 and column 1. So either row 1 or column 1 is a good choice to make your dominant row or column. All right, so I'm going to choose column 1. So that's why I highlighted it in yellow so that you can see that that's going to drive the rest of the work that I do. So 0 is in a positive position. That's because of this. Okay, so even though you don't have to write it, this will be a positive here, and it'll be 0 times, and then you're going to put a 2 by 2 matrix that are the numbers that are left when you eliminate the row and column that 0 is in. 0 is in column 1, row 1. So the numbers that 0 that are not associated with row 1 or column 1 completely like in a different position are the ones that you see here, -2, 1, and 3, 4. So that's what you write right here. Now we know how to evaluate 2 by 2 matrices, so we'll do that on the next line, but let's move on so you can see what to do next. My next number in the column is 2. 2 is in column 1, row 2, and that is in a negative position, which is why here I have a negative -2. And then you want to write down the numbers left in the original matrix that are not associated with column 1 or row 2, because that's where 2 is. So the numbers that are not associated with column 1 and row 2 are 1, -3, and 3, 4. That's what you see here. Okay, so now we go on. And so again, column 1, the third position in that column is 5. And 5 is in a positive position, right? Column 1, third row. So that's why here I have a plus. And then 5 is going to get multiplied by the matrix that has the numbers that are not associated with column 1 or row 3. So what are the numbers that are not associated with column 1 and row 3? Well, that's the ones that are left right here. 1, -3, and -2, 1, which is what you see here in that matrix. Okay, so you might want to rewatch that if you didn't follow, but they would all be set up in a similar way, keeping in mind that you are putting the sign in front of the coefficient, and the coefficients are determined by this, the column or row that you pick. The signs are determined by this plus and minus guide that I put up here. And then the sub-matrices, these 2 by 2s that I keep writing down, those are just the numbers that are left in the matrix when you eliminate the row and the column associated with the coefficient. So like in this example, I eliminate row 1 and column 1 associated with 0, which is why I'm left with -2, 1, 3, 4. Okay, so now that we have all of our 2 by 2 matrices set up, now remember how to evaluate a 2 by 2 matrix is you multiply across from left to right, and then multiply across this way from right to left, and you subtract the result. So that's what you're seeing on this line. It'll be 0 times -8 minus 3 minus 2 times -4 minus -9 plus 5 times -1 minus 6. When you do all of the subtractions inside of the parentheses, you'll get this result. So the first product is just 0, so I'm just writing 0. Then you have -2 times 5 plus 5 times -7. Well, that gives you -10 minus 35, which is -45. So we got the same answer that we did above with this method because it was the same matrix. So the second example in blue and the third example in orange had the same 3 by 3 matrix. I just showed you two different ways to find the value. Either way is fine. You should just use the method that seems easiest to you. All right, so now we're going to solve a system of linear equations with 3 equations and 3 unknowns using Cramer's rule. Remember, we used Cramer's rule on a 2 by 2, and now we're going to do this on a 3 by 3. So the rule is a little bit more complex, but it's not bad. It just takes quite a bit of space in your notebook. So just keep that in mind if you're writing things down. So here we have a system of 3 equations, 3 unknowns. The unknowns are x, y, and z. A, B, C are coefficients of the x, the y, and the z respectively. And D is our constant. So I have subscripts. So A sub 1 x plus B sub 1 y plus C sub 1 z equals D sub 1. That would be considered equation 1. And then I have a similar notation for equation 2 and 3. All right, so here's your Cramer's rule. You're basically going to be evaluating 3 by 3 matrices. And so here's the rule for x, y, and z. Let's start with the denominator, because the denominator will be the same when you compute x, y, and z. So once you do it for one variable, you don't have to repeat the process. So the numbers that go into the 3 by 3 matrix for the denominator are basically the coefficients of x in a column, the coefficients of y in a column, and the coefficients of z in a column. So that's why I have here in this matrix a sub 1, a sub 2, a sub 3 in column 1, b sub 1, b sub 2, b sub 3 in column 2, and C sub 1, C sub 2, C sub 3 in column 3. Now let's look at the difference between the bottom matrix and the one on top. So it looks almost the same except for the first column. The first column, because column 1 is associated with coefficients of x, right? That's the one that we see right here. That gets replaced with the constants, which are called D sub 1, D sub 2, D sub 3. Make sure you put them in the right order. Once the top determinant is found and the one in the denominator is found, then you just divide those two numbers, and that gives you the solution for x. Similar result for y and z. Let's talk about y first. Because we're solving for y, that means that the b's get replaced with the constants of d's, but everything else stays the same. The denominator is the same. The column A, the x column or the a's remain in their position, and the c's remain in the third row. And then when we solve for z, again, the denominator is the same all throughout, but in my numerator, the column that gets replaced is the one associated with z, which are the c's, and those get replaced with the constants of d1, d sub 1, d sub 2, d sub 3. All right. So there's a pattern here. Hopefully you see it. So let's use this information to solve a system of linear equations by Cramer's rule. Now, for purposes of saving space, I'm going to compute the denominator first because it will be the same number that will be used to solve for x, y, and z. So here's our 3 by 3 matrix. So we have 3 equations with 3 unknowns. So notice that in the second equation, I don't have an x term, but that just means that the coefficient for x is 0, and that's okay. All right, so we're going to write down all of our coefficients for my variables. So in the first column, first row, the coefficients of x, y, and z in equation 1 is right here. That's 1, -1, and -1. The coefficients for the second row, so that's equation 2, is 0, 4, and 1. And the coefficients for the third row in the determinant are found in equation 3. That's -1, 1, and -3. So I'm going to use the first method that I showed you, which is to repeat columns 1 and 2. So that's what I'm writing here. And then we just multiply across. So the first product of 3, this way, 1 times 4 times -3 is -12. Then -1 times 1 times -1, well, that gives you a +1. And then again, when you're going in this direction, you're adding. So -1 times 0 times 1, well, that's just 0. When you go in the other direction from right to left, -1 times 4 times -1, that's when you start subtracting. So that's -4. Then 1 times 1 times 1, well, that's -1. And then -1 times 0 times -3 is a result of 0. So when you compute those sums and differences, you get that your denominator is -16. Remember, that's not an answer. That's a number that we're going to divide the top matrices by, or the determinant of the top matrices by. So let's figure out the top matrix. So I'm going to call it D sub x to show that it's the top one associated with x. Remember that the only thing that changes in terms of writing down the matrix is the first column. The rest of it should look exactly like the matrix used to compute the denominator. So let's just go back to the original equation. The first column will get replaced with the constants. So that's what you see here, 2, 7, and 2. And the rest of it should look exactly like the denominator. So then my second column is -1, 4, and 1, and my third column is -1, 1, and -3. Remember, repeat columns 1 and 2. So that process is always the same regardless of what you're solving for. Always repeat columns 1 and 2 to the right of the matrix, and that's the trick to allow you to evaluate it. So when you evaluate, you start from the upper left-hand corner and go down on a diagonal. So you get these results here, -24 plus -2 plus -7. Then you start going in the other direction and subtract. So that's -8, -2, and -21. When you compute that result, you get that your numerator is a -48. Okay, but remember, that's not an answer. The answer is here, where your x is the determinant that we just evaluated, that I call D sub x, divided by the denominator that I call D. And those numbers were -48 over -16. So I have an x value of 3. Okay, so I'm going to repeat the process for y, but remember, to solve for y, I only have to do the numerator because my denominator will still be -16. Okay, so let's do the y. When you're computing the y, the x column and the first column and the third column should look exactly like your denominator. That part stays the same. The part that changes is column 2. Column 2 gets replaced with the constants, the numbers to the right of the equation. All right, then I'm going to do again that same trick. Repeat columns 1 and 2 here. So first you write down your 3 by 3 matrix, then repeat the first column and the second column to the right, and then we start that multiplication on a diagonal. So starting from here, 1 times 7 times negative 3 gives me negative 21. Then going over to the next one, 2 times 1 times negative 1 is plus negative 2. And then going to the last one, negative 1 times 0 times 2 gives me a product of 0. Then we go in the other direction, and this time we start subtracting. So negative 1 times 7 times negative 1 is a minus 7. Then 1 times 2 is a minus 2. Then 2 times 0 times negative 3 is 0. So you get a result of negative 32. Again, that's not a solution. You still have to do the division. So the value of y is the determinant you just evaluated, d sub y, divided by the denominator, which was negative 16, and your result is that y is 2. Okay, so we're going to do this one more time for z, and once you practice this a few times, hopefully you'll get really good at it. Because we're solving for z, this time the denominator matrix only changes by the third column, right? The third variable in the equation, therefore it's the third column. So that gets replaced with the constants of 2, 7, and 2. And then again, once you have that 3 by 3 matrix, repeat columns 1 and 2 to the right, and then we start multiplying on a diagonal. All right, so the first product is right here. 1 times 4 times 2 is 8, plus negative 1 times 7 times negative 1 is 7, plus 2 times 0 times 1 is 0. Then we start subtracting. So it's minus 2 times 4 times negative 1 is negative 8, minus 1 times 7 times 1 is negative 7, and then minus negative 1 times 0 times 2 is 0. Okay, when you compute that result, you get 16. And again, that's just d sub z. So then you still have to compute z by dividing that determinant, d sub z, by the original determinant, the denominator. So that was negative 16. 16 divided by negative 16 is negative 1. Therefore, we have a solution of 3, 2, and negative 1. Okay, so here we have another one. We want to solve this system of equations. So the 3 equations are here at the top. And again, we're going to first find our denominator so that we can use Cramer's rule. And so the denominator will be used to find x, y, and z. And so first you just put the coefficients of your equations in this determinant. So let's look at equation 1. So the row associated with equation 1 is 1, 1, negative 1. Those are the coefficients of x, y, and z. The row associated with equation 2 is 1, 2, negative 3. And then the row associated with equation 3 is 2, 3, negative 4. Then you repeat columns 1 and 2 and then multiply. All right, so the first product is 1 times 2 times negative 4, that's negative 8, plus 1 times negative 3 times 2, that's negative 6, plus negative 1 times 1 times 3, that's plus negative 3. Then we go in the other direction and you are subtracting. So negative 1 times 2 is minus a negative 4. Then 1 times negative 3 times 3, that's minus a negative 9. And then 1 times negative 4, that's minus a negative 4. So in this line, I just rewrote plus a minus, plus a negative to become a minus symbol, and then minus a negative to become a plus symbol. And then when I did all of my computations, my denominator works out to be 0. Now, we know that division by 0 is undefined, but that doesn't mean that there isn't a solution here. We really have to go one step further. We have to compute either d sub x, d sub y, or d sub z. It's definitely not going to be an independent system where we will get 1x, 1y, and 1z, but it could either be an inconsistent system or a dependent system, meaning inconsistent would be no solution, and dependent would mean infinitely many solutions. But let's see what we get for d sub x. So remember, to compute d sub x, column 1 gets replaced by the constants, 0, negative 3, negative 3. So if we go back to the equations, that those were the constants to the right of the equal sign, 0, -3, -3. So that replaces column 1. The rest of the matrix should look the same. Repeat columns 1 and 2, and when you do the computation for that, you get 0 again. Now, that means something special. When you get 0 over 0, that represents a dependent system, which means there are an infinite number of solutions. So the tricky part about dependent systems is knowing how to present them. So there's lots of ways to do this. I'm going to do something that's consistent with what the homework is expecting you to do. So, so we're going to let z equal some number t, and t could be anything. Then we're going to represent x and y in terms of t. So we'll have to do a little bit of algebra to do that. So in order to express x and y in terms of t, you're going to have to eliminate one of the variables so that you can solve for one variable in terms of z, and then we know that z is equal to t, because that's just something that we're just going to assume. All right, so in order to eliminate one of the variables, I'm going to subtract equations 1 and 2. And when I subtract equations 1 and 2, the x's cancel, okay, which is good news because now I have this new equation here that only has a y and a z in it. So when you solve it for y, that means you have to subtract 2z from both sides, which is what you see on the next line, and then multiply both sides by -1. So y is equal to 2z minus 3, but remember, z is t, so therefore y is 2t minus 3. All right, so now we have expressed y in terms of t. Okay, but now that we know that y is 2t minus 3 and z is t, we're going to plug it into one of the original equations, and I'm going to plug it into 1. It doesn't matter if you pick equation 1, 2, or 3, you will get the same answer. So I'm picking 1 because it's just a simpler equation. So this is equation 1 as a reminder. And I'm going to replace the y with 2t minus 3 and the z with t, which is what you see on the second line here. And then you want to combine like terms. And when you do, you'll get the third line, x plus t minus 3 equals 0. And then finally solve for x by subtracting t and adding 3. So now you have expressed all 3 variables in terms of t. So your infinitely many solutions where t could be any real number is -t plus 3, comma, 2t minus 3, comma, t. And that's considered to be an ordered pair, but again, it represents infinitely many ordered pairs that satisfy the system. Okay, so I'm going to do one example by elimination, not by Cramer's rule, just to give you a different perspective. And again, this is would be your choice which one you use. So we have this example here. Remember, with elimination, the goal is to add or subtract 2 equations in order to eliminate a variable. But because we have 3 equations and 3 variables, we're going to have to do that process more than once. All right, so here's our example with 3 equations, and I've labeled them 1, 2, and 3 here on the right, just so that we can follow along. So the first thing I'm going to do is make a decision as to which variable I want to eliminate. So really, any of them would be pretty easy to work with. So I'm just going to eliminate the x's by subtracting equations 1 and 2. So that work is here below. So I have equation 1 minus equation 2. And when you're subtracting, that means that all of the signs in equation 2 will change. So you get this result here, which is -2y minus 2z equals -14. I'm going to call that equation 4, again, just so that I can talk about things more easily. So now I need to do the same thing, eliminate the same variable using 2 other equations. So either I can use 1 and 3 or 2 and 3, and it doesn't matter which one you choose. So I'm going to multiply equation 1 by 2 and then subtract equation 3. By multiplying equation 1 by 2, the first term will be 2x, and when I subtract it from equation 3, the 2x's will eliminate, which is the point. All right, so that's the work I'm doing here. This is my new equation 1 when I multiply by 2. And here I'm showing you that I'm subtracting it from equation 3. And when you do that algebra, you get y plus 3z equals 11. And I'm going to call that equation 5. So notice that equation 4 up here and equation 5 here now have they're now two equations with two variables. And this is what we worked with in the previous section. We know how to solve equations with two equations and two variables. And so we need to eliminate again. And so that means you have to eliminate either the y or the z, and it doesn't matter which one you pick. So it looks like I've decided to eliminate, let me see what I did here. I'm going to eliminate the y's because I'm going to multiply equation 5 by 2 and add it to equation 4. So remember, if this becomes a 2y and I add it to equation 4, my y terms will get eliminated. So, so that's a good option. So that's what I did here. This is my new equation 5, 2y plus 6z equals 22. And here is my equation 4. That didn't change at all. I'm just writing it down. And when you add those two equations, the two y's cancel, and you get 4z equals 8, and therefore z is equal to 2. Once you get one solution, you're really just substituting back to get your other values for y and z. So I need to substitute z equal to 2 into either equation 4 or 5. So either this equation or this equation will now allow me to solve for y. So I chose 5. So that's the work you see here. Y plus 3 times 2 equals 11. So that means y has a value of 5. And once you know y and z, then you go back to the original equations and you can choose any one of the three, equation 1, 2, or 3. And I chose equation 1. So you plug in y equal to 5 and z equal to 2. Those were our previous two solutions. And solve for x, and you get that x is equal to 2. So this is an independent system with a solution of 2, 5, and 2. And you should always go back and check that your solutions work. And the way you know that you didn't make any mistakes is if you substitute 2, 5, and 2 into these three equations, the left side should equal the right side. If it only works for one equation, then it's not correct. If it works for none, it's definitely not correct. It has to work for all three equations. All right, so now you should try the homework. You really can solve with any method you prefer. So good luck.